let me recall what we're doing. So we're trying to define a set of relators, a set of defining relations for Burnside groups. So we start with we set the set of generators. Then we start with the free group with this basis, and we're trying to define a set of defining relations, so which are subdivided by subsets into subsets indexed by rank. So we have this one, G alpha minus 1, and this is a quotient, and I just because we use periodic relations, then all relations are of the form x to the n. So this is a normal closure of x to the n, where x runs over some set E alpha. So when sometimes the elements of the set are called elementary periods, so like due to Novikov-Hadian market, some call it periods of rank alpha. Anyway, so just we have this picture. Okay, and we need to define these sets E alpha. So alpha starts from 1 and so on. And we need to define the set E alpha in such a way that, first of all, G alpha. So we need two properties. G alpha is a small cancellation over the previous one. And but this is not enough, of course. And in the limit, we have to get all relations of the form. So it's G infinity, which is just this group. So we just take the union of all relations x to the n. X runs over the union of all the sets. So it should be the whole Burnside group. So all elements in the group should have an order which divides n. So this is two properties we need, and there are several approaches to a procedure. So actually this is a procedure. So this procedure goes as follows. So at any step we have this group G alpha minus 1, and once we know this group, we define this set, the set E alpha. So procedure, and actually we have two different approaches. So one is metric approach. Another one is depth approach by depth. So actually, metric. I explained that it was some. For example, it's used by Olshansky. Actually, I explained that it's in a similar way. So it's a similar idea. They use the Gromov-Devzant. So depth approach, it was originally used by Novikov-Hadian. Actually, I used it as well in my paper on even cases, on even exponent. Anyway, that's and I explained the last time that this approach could be could simplify things, but it needs very large bound on the exponent. So this is more effective from the point of view on the bound of the exponent, but it needs more complicated induction, because it needs more reference to inductive hypothesis. So it's in this sense it's more complicated, because it's easier to understand an inductive proof where, for example, we have only one inductive hypothesis. So it's easy to understand an inductive proof when we have say 2, 3, or 5 inductive hypotheses. But here we need several, I don't know, that's maybe several tens or something. At least several tens or something like this. Okay. So so an example of the metric approach. So it could be very simple. So metric, an example. So once we have this group G alpha minus 1, then we consider X. So for example, we can for this set E alpha, we can take a single element. So it was actually in the original work by Orshansky. So some single element, and we choose for X alpha some, so A, shortest word, which represents an element of the infinite order in the previous group. So the shortest word such that, so if we consider this group generated by this, this group generated by this element in the group G alpha minus 1, so it should have an infinite order. Okay, and so it's this clear procedure. So the only thing we have, which can vary here, that's we can take any shortest word. So we don't care about the order in which we take this. But okay, it works, and it works for at least for odd n greater than 10 to the 10. Okay. So this is an example, and the simplest way. Actually, I would like to describe today what does it mean to be what is this depth approach. So I have to recall a statement which could be called overlapping periodicity lemma so we have to formulate it. I need a simple notation. So if we have a word, then the set of periodic words with period x is just all subwords of all powers of x to the t. So consider this notation. So any subword of this word is called periodic word with period x. So suppose we have two words, x and y, and suppose we have a word which is periodic with with respect to both of these periods. So we have if say w belongs to this is periodic with period x, and at the same time is periodic with period y, and w is sufficiently large, so and W, the length of W is greater or equal than the sum of lengths of x and y, then actually we have the same periodicity. So up to cyclic shifts, x and y. So the point is that if we have a word x and we have, if we take any cyclic shift, then it's the same thing. Then there are some for cyclic shift.
So here x and y are not periodic words, right?
Okay, they could be.
Like y can be power of x.
No. Yes. Y can be power of x. And say I mean x prime of x and y. We have, so they are common powers of the same word. So x prime is equal to some z to the p, y prime is equal to z to the q for some z, and so and actually this of course implies that these sets are the same, so we have the same periodicity here. So this is a quite well-known thing. And okay, let's now take the following. Fix some number. Say some p. For example, say p 100. So what we could have here. So suppose we have this W, and the length of W, say the greater of if the length of W, say greater of P y, right? Then what can happen here? Then either so this is it can happen that this is the same thing as stated in the lemma. So okay, actually no, I have to okay. If you assume that x and y are non-powers. So this is what you said. This means that then so x is a cyclic shift of y. Let's just denote it like this. Okay, so actually I will be considering cases when I take the set of periodic words and the period is a non-power. So if assume that x and y are non-powers here. Now if we have this one, then either word, then actually it is small, say less than 2x at least. Okay, and this is one case, or otherwise they are cyclic shift of each other. Okay? You see from just from the lemma. So we have a common periodicity. So we have a periodic word, and this periodic word is okay, has sufficiently, so has p periods with p some constant, has p periods, contains p periods of some period. Then if you take another period that either it is the same period, or it cannot contain two other periods. So this is just follows from lemma, assuming that x and y are non-powers here. So in the first case, we see that w is has more than at least p periods of y, but less than 2 periods of x. So we see that the length of the size of y is much less than the size of x. So in the first case, we have the length of y is less than 2 over p, the length of x. So y is small compared to x. So we define, say y. So we produce this relation. In particular, because we have this inequality, then x cubed contains contains a periodic work with period y. Okay, let me just let's say it in this just write it this way. It's not quite precise, because actually it contains a word which is periodic with period p. It contains at least p periods. I just write it in this way. Okay. So x cubed contains. Okay. So what we do is the following. So consider now. Okay, let's consider all non-powers. Consider the set of all non-powers and cyclically reduced, of course. Cyclically reduced words. And consider the set of, so this is, okay, we see from this, it's actually a transitive relation, right? Because x cubed contains y to the p, and of course if we have this, another y1, which is which satisfies this inequality with respect to y, then of course we have the transitivity here. So which are minimal with respect to these relations. So consider x, the set of x, such that x is a non-power, cyclically reduced, and we have no y, which means okay, no. Okay, and so x are denoted by E1. So this will be E1 as we want to define here. Okay. So what can we say? Actually, from the construction we see that we have a small cancellation. If you consider this group G1. X to the n equals 1, where x runs over this E1. This is a small cancellation group in the standard small cancellation, in the usual sense. Small cancellation with what? With C prime lambda, where lambda is what? Actually, is it just P over n? Why? So what I claim here. So consider two. So all relations are of the form, and we have to consider. So we have to check this small cancellation condition. So we have x1 to the n. Okay, okay, we have two. So we have this xi to the SI-TI, actually STI, where, so we have two relators of this form, and we have a common initial segment of this relation, so we have to check. And the condition says that S is greater or equal than lambda of this size, x1 to the n. So it's precise. It's p. Right. So if we have this, then we compare this x1 and x2, and we use this in these properties. So we have either in this case x1, we have x1 less than x2, or they are cyclic shifts of each other. In the case where cyclic shift of each other, because they start with the same. Because these words are start with both x1 and x2, then we have either this one or just this one, just equal. And if you have equality, this is precisely what the small cancellation requires. But this case is impossible because we assume that we consider all minimal. So we have this small cancellation condition. This is okay. This is what we want here. Okay. Now we need E2. So we try to do the following, the next step. So of course we have so all minimal x with respect to this relation are now belong to E1. So if we have an element of infinite order in G1, this implies that so first of all we can consider reduced with respect to G1, and we can consider non-powers with respect to G1. And if you have an element of infinite order, then it can be reduced, it can be represented as a power or some non-power element, and this non-power element should not belong to E1. So it should be not minimal. Okay, so we define the following thing. So consider a period over G1 by definition is a word reduced a word. So it is a word x such that first of all it's a non-power reduced in cyclically reduced. In G1 I call it in rank 1. So everything, if every element of infinite order can be represented by a cyclically reduced word. So this is a statement from which this is a consequence of the small cancellation theory. And what is okay? This is just a definition. So and we know that we for taking this at E2 we need to consider only periods over G1. Okay. So and we introduce a similar relation. But if you remember, with everything, if you increase the rank, then coincidence actually should be replaced by closeness. And we have a similar thing. Let's define a similar thing. So we say that define on the set of periods. On the set of periods. Okay, on the set. Let me make a simple observation first. So because we have this one, cyclically reduced means at least reduced. So it's if you have a period over G1, then it belongs to this set, of course. It's a cyclically reduced word which is on the power with, okay, as it is, and because all minimal words in this set are taken to E1. This implies that every word from this set is not minimal. So this means that for any period of over G1, there is, for any period x over G1, there exists y such that, so there's every period actually contains in this sense a p power of another period. So this is an important observation. But now what we do, we define another relation. So let me call it, say, y. It's a similar way, but I put a 1 on the top, which means this has rank 1. So this one will be rank 0. And now I define another relation which I call rank 1. Let's rank 1 much smaller. Okay, let's say it in this way. So in the same way, x cube contains has a subword say S such that I don't like S, I don't know, so it's a subword W such that W is close in rank 1 to y to the p. This is not quite exact actually. It's not. So it's just. I would like to represent an idea. It's not precise, because I have to take a periodic word. Okay. No. Let me be more precise. To some. To a word Z. Have the rule. Let me. X cube is equal to say x1 w x2, and there exists say Z, which is periodic with period y, and the length of Z is at least p periods, p times the length of y. So Z has at least p periods of y, and W and Z are close in rank 1. Okay, I write it in this way. Okay. So instead of coincidence, I take closeness here in rank 1. Okay. What we have here? So now and in a similar way, we take E2 is the set okay. a set of such x's when x is a period over G1 and what? Null, and it's minimal in this with respect to this relation. Okay. Actually, we can generalize this procedure, and we can define so definition. We can define the following: a period over G alpha is a word is a cyclically reduced word which is non-power in G alpha minus 1. So this is the first thing. It's a similar thing. It's precisely like we generalize this. What else? We know what is cyclically reduced. This is defined with respect to the small cancellation theory, which we already know. So it doesn't contain subwords. Cyclically reduced means it doesn't contain subwords which are close to a big part of the relator. Power. So again, we have to define x on this set of periods. We define x is much smaller than y which is much smaller than x in rank alpha, which is by definition x cubed is in the same way x1 w x2. This is graphical equality, so just equality of parts. And there exists some z which is periodic with period y, and is big enough, contains at least p periods, and what we have, and W and Z are close. In which rank? In rank alpha. And so this is the next thing, and for E alpha, for E alpha plus 1. Yeah, for alpha plus 1. Okay. We take the set of all words x, which is a period over G alpha, and null, which is minimal with respect to this relation. So, actually, this is a real first approximation to the definition of what I call construction of set of defining relation for the Burnside group. But but this is a procedure by depth. So why this is depth? Because let's consider. So we have this one. We have this observation. So for any period of rank for any period over G1, any period over G1 contains actually a big power of some other period. So what can we say about I don't know. Let's consider a period over G2, like this one. Period over G2. Period over G1. a period over G1. It contains, so this is a cube of this period. Okay, it contains precisely. Okay, let's consider a period, let X a period over G2. Okay. So we have X cube. It contains a subworld. Let me put some color, which is closed by definition, because it's not minimal. It's not minimal with respect to the relation. It's not minimal with respect to the relation to this relation. So a period of rank 2 is a period of rank 1. So by definition, because each time we restrict the set of periods, and it cannot be minimal in this with respect to this relation, because otherwise it should be if it's minimal, then it should belong to the set of periods to the set of periods, and by definition it represents an element of finite order. So, period. Maybe cyclically reduced word, non-power. Actually, it should be better word such that infinite order. Every time I just explicitly write that it should be infinite order. Infinite order in this group. Let me write explicitly, because actually the point is every element can be made cyclically reduced. But we assume that it should be infinite order, and this is cyclically reduced non-power infinite order in G alpha minus 1. So let me write it explicitly. So if we have a period over G2, so it's a period it's a period over G1 by definition, and it's not minimal. It's not minimal with respect to this relation, because otherwise, it should belong to E2, and all elements of E2 have finite order. So this means that some subword of x cubed, which is say, I don't know, y1 to the p up to cyclic shift, and it's closed in which rank? In rank 1, because it's not minimal with respect to this relation. Okay. So, but you see, this is y1 to the p, and this means that it contains so this is a period of rank 1, right? And the period of rank 1, if this is a period of over G1, and the period of over G1 is such that every x cube of this period contains some p power of period of another word. So we have in this word we have many p minus 2 occurrences of some periodic word with period which contains some periodic words which contain p power of some other word. But the point is this. But the point is actually we have stability of periodic words. So this is what we have here. We have so okay, let's consider So I claim that actually x cube. Okay, let me. Okay, so let me. So in a general case, so suppose we have a period over G alpha. Yes. Okay. So this means that x cube contains some. So y1 is a period then over let's calculate is a period of over G alpha is a cyclically reduced but with not power infinite order, and actually it cannot belong to the set of it cannot belong to the set E alpha, and it means that it's not minimal with respect to this relation in rank alpha minus 1. And this means that it is close in rank alpha minus 1. A subrod of x cube is close in rank alpha minus 1 to some broad which is p power of a period of rank period over G alpha minus 1. This is the picture. Okay, so and now I introduce another definition. A coarsely. So I call this word. I call this which occurs in X cube. It's a coarsely periodic word. A coarsely periodic word over G alpha. And this is so it's a word. It is a word. Is a word such that reduced in rank alpha. This is always so I'll consider all the things reduced in the corresponding rank, and is close in rank alpha to a word, say Z, which is periodic with some period y, and y is a period over G alpha. So we have periods over G alpha, which represent infinite elements on infinite order in this group. So we have periodic words, and if you consider a closeness in rank alpha, then I get a set of words which are called coarsely periodic words. So the point is actually a coarsely periodic word. So in this case, we have a coarsely periodic word over G alpha minus 1. So over the previous rank. So if we have a period over G alpha, and then and consider consider x cube, then it contains a coarsely periodic word over G alpha minus 1. But so we can measure a number of periods in a coarsely periodic word. So in the following way. So we have closeness here, and you just measure the number of periods in this periodic part. I call it actually. So this is I call it a periodic base. So we have a periodic base for this coarsely periodic word, and we just count the number of periods. So we have coarsely periodic word here, which contains p periods. But actually, the point is, if we have a coarsely periodic word, so this is if we assume that we have a small cancellation theory, Then actually a coarsely, so this is statement position. A coarsely periodic p power contains over G alpha contains some p minus epsilon, some epsilon, I don't care, which is epsilon. So this some coarsely periodic words p minus epsilon powers over G alpha minus 1. So actually we have this so what we see actually not any k power, k minus epsilon. So why this is true? So if you consider this picture, so the point is actually so we have this closeness in rank alpha minus 1. So let's come back to this picture again. So consider a period over G alpha, and consider, for example, consider the word x cube. Well, this is the point. So let's consider this statement. So we have a k power over G alpha, which is a coarsely periodic. So we have a coarsely periodic k power over G alpha. This means that we have a period. X is a period over G alpha. Okay. We have a closeness in rank alpha. So this will be so x to the k, right? We have a closeness in rank alpha to this coarsely periodic k power. I don't know. It is called. I don't know. I don't know, Z. Okay, and we know that x to the k. Okay, no, Z, not Z, Z because we I don't know. U, no, U, X, Y, Z. I don't know, G. Okay. And we know that this word x to the k contains k minus 2 coarsely by definition. It contains k minus 2 coarsely periodic words with period coarsely periodic p powers, right? Over G alpha minus 1. This is by definition. So the point is that we have stability. So the proof of this goes as follows. So we have to consider two cases. So we know this structure of closeness relations. You see this? They have. So we can see that the corresponding diagram. Then we have some set of so-called active cells, and we have the set of active fragments here. So suppose we have some active fragment of rank alpha, because it corresponds to a relation of the form x to the n, where x is a period. But it's again. So this means that this x. This is x to the k. Okay, let's okay. I don't care. So this means that x contains a very big power, which is close to half of n of another period over g alpha minus 1, because it's period of rank alpha. So again, and this means that we can take this for this coarsely periodic power, which contains in x to the k, and there are as many. So there's approximately k minus 2 of them, because it should occur in x cube, and it is we have at least k minus 2 of them here. And for every fragment here, we have a corresponding image here, which is also if we have an active fragment. An active fragment is also some coarsely periodic power over g alpha minus 1. This is by construction. So we have many coarsely periodic powers over g alpha minus 1 if we have at least one active fragment here. If we have no active fragment, then we come to a relation. To come to the relation in rank alpha minus 1 in the previous group, and we use some stability property here, because we have actually coarsely periodic words of rank alpha, and we have equality in this group. So it means that they also have images. So we can each coarsely periodic word here it has corresponding image in this G. So again we have so k minus 2 or approximately k minus 2. Actually some k minus epsilon. So this my argument is not quite strict here, but so this is the idea. So if we have no active fragments here of rank alpha, then we can come to equality in the previous group, and this coarsely periodic words of rank alpha we can prove that they are somehow stable in closeness of rank alpha minus 1, and this means that stable means we have a similar image, similar coarsely periodic word, but with some loss actually. So this is the point. We always when we come from one word to another word in the closeness relation, that we always have some loss. Okay, so this is like a I explained why this proposition holds, and this shows that we have we have a procedure by depth, because you see, so instead of periodic words we have a coarsely periodic words, and every coarsely periodic word over G alpha contains approximately some coarsely periodic words of the previous group, and in turn, because we have p minus epsilon here, so each one contains in turn this number. So every coarsely periodic word of this here contains p minus epsilon of other periodic words over G alpha 2, and so on. So we have this means in this sense this means that coarsely periodic word over G alpha has depth, has this coarsely periodic depth, which is alpha here. So this is why this idea leads to the procedure which I called definition of construction of defining relations for the Burnside group by depth. So this is I think it's the right time to have a break. And I want to say that we have the following thing. So actually, this is actually first approximation. This if it define this sets precisely in this way, then actually this doesn't work. So we have to essentially adjust this procedure, and well, I try to explain actually maybe in the next half why this exact procedure doesn't work. So this is a very important thing that in this way this doesn't work, and say all the extra stuff in the paper, say by Novikov and Agdian, actually more or less was created to overcome this abstraction which doesn't allow to define this set simply in this way. So this is okay. So let's have a break. I had to say, first of all, I have to formulate like a generalization of this overlapping periodicity lemma, the generalized form of this, because actually I use it implicitly at least here, because if I say okay, I use it. Actually, okay. Let me formulate this general form of this more general form, generalized form of overlapping periodicity lemma. Generalized overlapping periodicity lemma. It's a similar thing. Okay, it's precisely just we replace coincidence by closeness. So suppose we have a xy. So let xy be periods over G alpha. And so instead of let me formulate it in the following way. So we have some x to say some big N is equal to S. Okay, now xy. Let me take x2 and x1 and x2. Yes. And xi to the n is a si ti. Okay, some big N. So this will have a big power n here. I don't care which one, but actually we have a periodic word. But okay, I assume that we have these two periodic words, S1 and S2, and instead of coincidence here, instead of W, we have a closeness of two words. So Si, S1, and S2 are close in rank alpha. And let's say that each of the words Sy is at least two periods. In this form, when I use this form, then actually, okay. But moreover, let me write this closeness explicitly. S1 is equal to U S2B, where U in G alpha, where you remember how did I define closeness here? So just take this equality, and I assume that UV are some small words which are called bridge words. So UV, and this by this set I denote these bridge words. So this is closeness relation. And assume that each of this SI contains at least 2 periods. Then okay, we not claim that X and Y are powers of the same element up to cyclic shift, because I already assume that they are not non-powers, because periods means non-powers. So actually I have this strong form. This actually we have not cyclic shift, but we have conjugation here. So then S1 is equal to U S2 U inverse in GF. So this is the form. Actually, it's not quite precise because okay, I have to in precise form. It's formulated a little bit in different way, but it's like a good approximation to this. And you see that it's the same thing that we replace the coincidence just by closeness, and that's it. Okay, and actually, if you look at this and we compare with this small cancellation condition, which if you remember, this was formulated small cancellation condition instead of periods of so this actually this implies it's not implies. It doesn't imply actually explicitly, but okay, we can use here. We can use this part of the board. So consider now two periods like this, and assume that in the small cancellation condition, we assume that one of the SIs is large compared. Okay, you remember this. In the small cancellation condition, we have this one S1 alpha is greater or equal lambda of the size of the relation x1 to the n in the small cancellation condition. And it should imply the small cancellation condition precisely what is written here. So the small cancellation condition says the following: let x1 and x2 be so okay. So this is I have to adjust rank here. Actually, this small cancellation for rank alpha plus 1. It should imply the following. Consider two relators of rank alpha plus 1. You see that if you every small cancellation condition is formulated for the particular value of rank. So this is which formulated for each value of rank. So this corresponds to the small cancellation condition in rank alpha plus 1. Because if you remember how it's formulated, so it says the following: if we have consider relators of rank alpha plus 1, right? So we have x to the 1 to the n and x2 to the n, in where x1 and x2 belong to this set, right? This is because the relators are of the form here. So, and we have an initial segment of each xi to the n, to the small n. So this is just more general case here. And we have the closeness here in rank in group G alpha. This is, and the only thing which is required in the small cancellation, instead of this one, instead of this both we have this one. But actually it's equivalent. It's equivalent to So because we have this periodic word, so this is the same as S1, something like lambda minus. Okay, let's if lambda if n is big enough, so this implies that like this. So this means that Si contains some large number of periods here. So and in this case, you see, we have to if you know that this if you prove this lemma, then we can have two possibilities precisely in the case of like we consider two cases after this lemma here. So there are two cases. We have either S2 is greater or equal than 2. So S2 is big enough here. And in this case, we have we apply this lemma and conclude that S1 and x1 to the n, not S1, x2 to the n. So relators should be conjugate. Actually, periods should be conjugate. Sorry, this is a mistake here. Periods are conjugate. And so there are two cases. If we have this equality, then we use this lemma and conclude that periods are conjugate, and this implies that n's powers are conjugate. This is precisely what we require in the small cancellation condition. So this is small. But if you have this one, then we get the following, that we have precisely this relation. So we have precisely what we have. So x1 is much less in rank alpha than x2. So in this situation, when we try to prove the small cancellation condition, we have either this, then this small cancellation condition holds, or we have this one, and in this case, then we have x1 is much less than x2 in rank alpha. So we have precisely this relation, and this means that x2 is not minimal. Is not minimal, and this contradicts this definition of E alpha plus 1. So if x and 1 are so that if x1, x2 belong to this set, then we this generalized overlapping periodicity lemma implies the small cancellation condition. Okay. So this is actually this is precisely how it works. But the thing which I want to explain. So why this looks very good. So because this implies a small cancellation condition. But why this doesn't work actually? So what's the problem here? The problem is in the other part of the small cancellation condition. So if you remember, the small cancellation condition consisted of three parts. The first part that we consider periods relators which are reduced, cyclically reduced. The second part we consider that they should be big enough, they should be large enough compared to the corresponding group. So we should have this relator. So we have this, if we have x belong to this set, so I consider this small cancellation for this value of rank, then the size of with respect to the rank alpha of this relator should be bounded from below by some constant. This is part of my small cancellation condition. It consisted of three of three conditions. One was cyclically reduced. The another one is like relators are big enough, and the other one is precisely the proper small cancellation condition when we consider two close subwords of relators. So this one we should check, and it turns out that with this definition, this inject, so we cannot prove this. We cannot prove this. What's the problem here? So let's recall how we define this size. So we have a word, say W. How we calculate this length in rank alpha. So we represent W. So we partition in the product of some subwords, and where Wi is a subword of a fragment of rank beta, which is less or equal than alpha, and or we also admit letters or letter or a letter. And if so we can consider if it's a letter, then we assign like consider it like a fragment of rank 0. So this partition we call the fragmentation. This is a fragmentation. Rank alpha. And if we have a fragmentation, say F, then we have to define the weight of F in rank alpha. So we count. So this is say M alpha plus say zeta M alpha minus 1 plus and so on plus zeta to the alpha M0, where M alpha is a number of subwords of fragments of rank M beta, of rank beta. So we count. So we partition our words into subwords, and each subword is some subword of a fragment of some rank of not greater than alpha, and count this. So each M beta is number of such subwords of fragment of rank beta here. And if beta is equal to 0, we can also we can use letters here, and if we have a letter, then we assign to the letter beta. So this M0 is just the number of letters in the partition, number of letters in the partition. So and by definition, the size is the minimal possible weight. F is a fragmentation of rank alpha of
is zeta a new parameter?
Zeta is some number. Actually, I take this is some constant. Actually, I consider this 1 over 20. So it's some. So okay, we partition our words into pieces, and we assign a weight to each piece. If we have suborbital fragment of rank alpha, this is maximal weight, which is 1. If we have a fragment, a suborbital fragment of rank alpha minus 1, so we count this word with weight 1/20, and if we consider a letter, just a letter, then it counts with weight 1/20 to the alpha.
Was it called length?
Okay, size, length. Okay, this is
I think in the first.
length.
Yeah, maybe.
I don't remember how like length. Okay,
But
length.
it's the same thing.
It's the same thing. Yeah. Okay. So, and I want to. So this is actually this again. This is an important an important thing here, because it measures words in fragments. So if you just consider if each W just consider just a letter, then we have a very small weight for letters. Okay. And we need to check this one. So x, if we have this elementary period, let me call it in this way, and we have this and we have the corresponding relator, then we have this one. So we need to check this.
And each word of relator of rank alpha contains which number of periods in the previous rank, or P? Or
P,
P.
yes.
And P is
P by P minus epsilon, a coarsely periodic word with.
Yeah, but how big is P? P.
P fixed.
P some number actually. It's about 100, but actually I don't remember the precise value.
So
like actually it's in the real proof it's I think it's 80, but okay it's.
But it should be bigger than 1 divided by 7, right? Because we should prefer big pieces of rank alpha.
Here we have n here.
N.
This is big N. So the x to the n contains many such.
Yeah.
And okay, let's look at the picture now.
But even if we contain just not a whole relator, but a piece, we still want this piece to be considered as a piece of rank alpha and not a bunch of alpha minus ones, right? In this weight, the first term should be used, right?
So I didn't catch.
So if we have just one period.
Okay, x just one x, right?
Yes, well, yeah, one element of this E alpha plus 1, then the weight will be, what will be the weight?
We don't know. Let's try to understand.
Okay.
Let's consider x to the n, right?
Mm-hmm.
And we know that x to the x cube contains some coarsely periodic word of rank contains is it written here or it's erased? It's probably erased. Okay, contains some pi minus epsilon. I don't care about constant, but pi minus epsilon should be actually like 50 or something like this. Power coarsely. Power with period over okay, of course the power over G. So if it's considered to this E alpha plus 1 like this, it's period over G alpha. and the period over G alpha contains P minus epsilon power of G alpha minus 1.
So it's a statement about x cube.
X cube. Okay, but I don't know, so we don't care. So it's X cube, but it's small compared to the x to the n. So it contains many such powers. So x, this like, I don't know how to know it. W, right, it's W exactly. Contains W. So we have this here W, here W. And the point is that it's close to some, close in rank alpha minus 1 to some p power, y to the p. Yeah, precisely like this. Okay. What's this? So assume, so we have to cover this x to the n by the subwords of a fragment. So suppose we have a subwords of a fragment which is subword of this word. I don't know. So what's the picture? So this is the subword, and because it's okay, it's subword of a fragment, like, which means that we have a fragment. Okay, this is the picture. So, this is subword and this is fragment. This is why I remember I draw it in blue. This bridges, and it's close to. It's close in rank, so it's subword of a fragment. Okay, let's assume that it's subword of a fragment of rank alpha. So we have alpha minus 1 again here, and this is a part of relator of rank alpha. So it's some z. So this is the picture. So it's a word of a fragment. It means that this word is close to some piece of a relator, but the relator of rank alpha. So this is. But I claim that this cannot be. So this subword cannot be more than p of p periods of x. Why? Because it's greater or equal than p. So what we have here, then we have that we have here. Then p or maybe p plus epsilon. Yeah. Maybe p plus epsilon. I'm not sure. Because if it will be greater or equal than p plus epsilon, then so we can actually take a little bit take with some loss. We can draw a small piece of x, fx to the p, which is close to some periodic word with period which belongs to the alpha, but this will imply that z is not minimal with respect to this so we have z. So we have z. So x is much smaller in rank alpha minus 1 than z. Because if you have this, if you assume that this piece, this part of x, this subword of x to the n is greater or equal than p plus epsilon, then actually we can make it a little bit smaller, and we can prove that a part of p is close. A part of the subword of this word which contains at least p periods x, is close to some periodic. So we can draw a little bit. We can decrease this closeness, and we can restrict it to a piece of to a part of x to the p. So that part which is greater than x to the p, and it's close to this port, and this would imply that x is much smaller than z. So this contradicts to the definition of this set. So in other words, so if we have if we cover x to the n like this, so if we consider a subworld of a fragment of alpha, precisely alpha, that it cannot cover more than this number of periods of x. So it's not, it cannot be, okay, it probably can cover x to the 100 periods, but it cannot cover much more. So, but the point is actually we consider, if we consider alpha minus 1 here, consider, so we consider the case when beta is equal to alpha, right? But if we consider the case if beta is equal to alpha minus 1, so subworld which is we consider a subworld of x to the n, which is a subworld of fragment of rank beta of alpha minus 1, for example, we cannot prove better than this. That's the point here. So again, we only can conclude that it cannot contain that p plus x, that something like p periods of x here. So we cannot contain that it covers a very small part of x to the n. So this is our definition doesn't allow to prove this beta bound if we replace this e alpha with alpha minus 1 and this is with alpha minus 2. So this is a real difficulty here, and okay, this is a, and so if we play alpha minus 1, so this is for alpha minus 1. If we play for alpha minus 2, this is the similar picture. So we cannot, and the point is that if we can cover this x to the n by very large number, but subworlds of fragments of a smaller rank, then because of zeta here, so we cannot reach this equality. So. And actually, there is a trick to overcome this difficulty. So the point is that so you see, let's see the procedure how we define the set of rods, which is E alpha plus 1. So we consider the set of periods over G alpha. Then we define some relation on this set, and we that's in other words. Then we consider that they define the set of elementary periods of the next rank, like by extracting from the set of periods. So by dropping out some x's which are not minimal in this relation. So if it's minimal, then we include it in this set. But if it's not minimal, then we drop it out, and and actually because we want that all words eventually should become should have an infinite order. Then this means that we leave it for the next for periods of the next rank. Next ranks, somewhere in the future. So and actually and I call it suspended periods over G alpha. So the set of suspended periods over G alpha are precisely which are not minimal. So it's And okay, what I do actually, I increase the set of suspended periods compared to this definition. So and actually I increase, I make the set of the set E alpha plus 1 smaller than this in this definition. So this called, okay, suspended periods of over G alpha of level level 0 by definition. So X is a suspended period over G null of level 0 if if there is Y such that so I call periods which are not minimal with respect to this relation suspended periods, suspended of level 0. And these definitions, if I just leave this definition without change, then actually this definition says that every elementary period of rank alpha plus 1 if is any period which is not suspended. But actually, the trick here, actually this is quite natural trick, is to increase the set of suspended periods. So there are suspended periods of level, say, of level k, say. So we have suspended periods of level 0, and with so very roughly we have the picture like this. We have, for example, a closeness relation. So we have a close. So X is a suspended period of level k if there exists suspended period of Y of level k minus 1 such that we have W1 is periodic with period X, W2 is periodic with period Y, W1 are closed in rank alpha, and X is not X and Y are not conjugate. X, Y are not conjugate. In G alpha, and we have closeness. So W2 contains at least, roughly speaking, 3 periods of Y. So it's not okay. It's not maybe not easy to explain. But again, we have this following picture. We have closeness in rank alpha. You see this. Draw it in blue here. This is W1 and W2, which is periodic with period Y. And it contains at least three periods of Y. But W1 contains, roughly speaking, it contains less than 2 periods of X. Because again, because of this overlapping lemma. So, you see, Because if you would have that each this W1 and W2 contains two corresponding periods, then we by this generalized overlapping lemma, these two periods would be conjugate. So if one contains three periods, at least three periods, then another one contains less than two periods.
Again,
So-
starting from the very beginning, we say that X is
Suspended periods of level k, if there is a suspended periods y of the previous level,
Mhm.
and we have closeness, so we have one periodic words which contains three periods of one periods,
Mhm.
is close in rank alpha to a periodic word which contains less than two periods of the other period. So y is a little bit less than x in some informal sense.
So there exists W1 and W2, and they are close, and but how are they related to
Because
X and-
W1 is a periodic with period x,
yes,
W2 is periodic with period y.
yes, but how are they related to X and Y? X and Y are not conjugated.
X and y, x, and so we assume that
Why is
x okay, we compare two periods, x and y, right?
Yes.
Okay, assume that there are two periodic words, one with period x and another one with period y,
Okay.
which are close in rank alpha, but the first one contains three periods, and the second one
Of
contains
X
less
and
than
X
two
of-
periods.
of Y.
So let's denote that relation like y. This is two. Okay, like y less than x. Little be less than x in some sense.
Mhm.
So actually, so this is relation. So you see, and I included. So first of all, I have suspended of level 0, and then if I have this, we have a suspended of level 0, and we have this we have this W1 and W2. Then I have suspended of level 1. Then I have suspended of level 2 and so on. And each time you see, if you have a suspended of level 1, then actually suspended of the next level are a little bit bigger than the suspended of the previous level. This definition is not precise actually. It's not precise. So instead of this three, actually I claim that instead of three periods, I claim that they should contain three occurrences of some three occurrences of some coarsely periodic word with another period. So it's not precise, but it's like it describes somehow the idea.
So does it mean that we have like so the rank of a period is now not a natural number but a tuple of
No. I define. You see, I define suspended periods of any level. Then, by definition, the set of all elementary periods is all periods except suspended ones. So I drop them out. So this is the point.
Okay.
Actually, I make the set of elementary periods smaller, and because I've made it smaller, so it can be proved that actually they satisfy this. They really satisfy this bound. This is one thing, but another thing actually. It turns out that because of some stability properties, of course, the periodic words, we have similar properties of every. We have this remains valid here. So every coarsely periodic k power over g alpha still contains this. So we have this. Okay, we have this depth statement about depth of periodic words. So this is it still holds here. So okay, and if you look at the paper by Sergei Ivanovich Adyan, where he tries to I don't know, it was about from 20, about 20 or something like pages in Uspekhi, where he tries to describe his approach, where he claims that he can prove he can describe the Burnside group for exponents like 101. So actually, he used this like procedure to define the set of elementary periods very close to what I described. Actually, I told him about this. And he tried to use it, but I understand. I realized that in this form, this low bound 101 cannot be achieved.
So you mean to define this elementary periods?
Yes.
He was also excluding some particular time.
Yes. So he described like this. So he has suspended of level 0 of level and he defines this suspended of level of the next level with respect to using the suspended of level of the previous level like this, and then he drops out all suspended periods. So this is a necessary thing. If we do not define the set of elementary periods of this way, then we need actually all this theory of transformation of worlds like normalized occurrences and so on. So this is the cascades and so on. So this is to avoid cascades actually. And this is to make all arguments just more or less geometric, not using this complicated combinatorial transformation arguments. So I think it's this is so what we did today. I explained very rough. So I explained this procedure of defining the set of defining relations using the depth approach. I explained how the proper part of the small cancellation condition follows from this. And I explained that actually we need to adjust. So I explained the idea, and actually I explained that we need to adjust this definition by adding the set of suspended periods here. So actually I think that's maybe all for this.
This is a good introduction to the paper.
For this introduction, yeah.
Show up.
So now we finished.